All right, so last time when we left off, we were talking about antiderivatives that involved basically 1 over x, right? And we found out, or we talked about this slide over here. The rule was, oops, I missed it, was that the antiderivative of 1 over x was the natural log of the absolute value of x plus c. And we talked about the fact that there are two different ways of dealing with items. One of them you'd seen before, u substitution, and you guys sort of looked at me like I really thought that I wasn't going to ever have to do that again. And then the second one that you really had never thought would ever in your life come back up again, which was long division, right? Mm-hmm. Yeah. And so we're going to take a look at another one that's an interesting one here today. So if you take a look at this one, you should notice a couple of things. The first thing you should notice is that there is an antiderivative here, and there's a natural log going on. The natural log that's going on right there, you don't have a closed derivative form for what is, antiderivative form for what is the antiderivative of natural log x. As a matter of fact, if you take your antiderivative sheet that I gave you, your integration sheet, it's not on there, okay? So the first thing you have to realize when you look at that is, well, evidently, that ln x can't actually be in there and me actually take the derivative of it, the antiderivative of it. So whenever you see a natural log and you're trying to take the antiderivative of it for what we're working with at the moment, and we'll talk about what to do with them otherwise later, that's u. Let me also just make one comment, is that you see a squared on the outside. This 2 cannot be put to the front of the natural log. Why not? Because it's on the outside of the natural log. It's not the natural log of x squared. It's the natural log of x squared. Does that make sense? That rule that we had before would have looked like this. It was the x that was squared, not the ln of x that was squared. So we can't pull the 2 to the front either. It just has to be what it is. I don't need it as a part of the u, though, because when I replace this here in a moment, I will simply replace it with a u here, and that u can be squared. So I don't need squared as a part of what u is. If I have u as ln of x, what is du? 1 over x, good. And that's the rule we had from section 5.1, right? And that's really good because you have a 1 over x dx in this problem, don't you? It's all right there. So that component gets replaced by du. I don't have any denominator anymore. The denominator, the part over x, that was part of du. So what is the antiderivative then of u squared? That's the derivative. The antiderivative. And this is 1/3 u. Okay. 1/3 u cubed, or you might remember it as u cubed over 3, which is the same thing, of course. Am I done?
Replace u.
I have to do that, but not yet. Plus c, good. And then I'll replace, like you suggested, Cameron, so I have now 1/3. U is natural log, so this is natural log of x. That doesn't look very good. Let's try that again. All of the natural log of x, those parentheses are needed, is cubed. And then we have plus c. Does that make sense? Okay. So you just have to recognize that when you have an antiderivative of a natural log, that natural log is part of what u is going to be. All right, so the last part of this section has to do with trigonometric integrals. And we looked at some trigonometric integrals last time at the very beginning. They weren't exactly the ones that you've seen before, but the first 2 were on that list. So let's fill those in. What is the antiderivative of sine x?
Cosine x.
Close.
Negative cosine.
Negative cosine x. Plus c, right? What's the antiderivative of cosine x? Sine x. Okay, so those are the same ones that we did last time. How about tangent? Well, you've never seen these before, all right? So I'm going to give you these, and these are going to involve, and it should come as no surprise, natural logs. That's why they're occurring in this section. So the first one, tangent, its antiderivative is negative natural log of the absolute value of cosine of x plus c. Cotangent's very similar. Instead of it being negative, it's positive. It's also natural log, but it's a natural log of sine of x plus c. Secant is the natural log, and this one's interesting. It's of the absolute value of secant x plus tangent x, and then all of that's plus c. Cosecant, similar. It's a negative natural log of the absolute value of cosecant of x. Didn't get that written right. Let's try again. Plus cotangent x. Absolute value ends, and then plus c.
Are we ever going to improve this?
No, I'm not going to ask you to prove them, although you certainly could. It wouldn't be that difficult. The way that you can prove that they actually work is you take the natural log that's on the right-hand side and you differentiate. You take the derivative. And when you take the derivative and simplify, it will become what's on the left. So it's not overly cumbersome to do. So what I want us to do right now is to apply these rules to similar functions. So whether that parentheses there or not, sometimes your book will put it in and sometimes it won't. It just depends. And so if it's clear without it, sometimes it leaves those parentheses off. So this is actually the secant of x over 2. This is one of those situations where you can turn it into u substitution if you'd like, and I'm going to show you that. But after you do a few of these, you're going to just recognize it and be able to handle it and not ever actually write it down, and that's okay too. So what would u be in this case? X over 2, which means what's du? Yes, 1/2, and then I tend to write it 1/2 du, but you can write it as du over 2 if you'd like. Yeah, not du, dx, yeah.
I changed it.
There we go. And then if we solve this for dx so that we can replace the dx that's here, we would multiply the 2 to the other side. So 2 du is equal to dx, which means I can rewrite my integration with the 2 in the front. I've got my integration symbol, secant of u du. So the 2 stays because it's a constant multiplier. And then I just gave you a closed form, that means an actual rule for what the antiderivative was of secant. So if you flip back to the page before, you'll see a secant there. And it is the natural log of the absolute value of secant of u plus tangent of u, close my absolute value, plus c. I need to do one more thing. What do I need to do? Yes, I need to substitute the u's back in as x over 2. So I have 2 times the natural log of secant of x over 2, with or without the parentheses, either way would be okay, plus tangent of x over 2, and then plus c. Any questions on that? Okay. B. What do you think? What would you try if you were given this problem? It doesn't look exactly like any of our forms. And it also doesn't simplify into a trig form, obviously.
Make u sine.
That's a good as a way to start. So you can take the denominator and make that u. So the denominator would be 1 plus sine t. If I do that, what is the derivative of 1 plus sine t? The derivative of 1 is 0, right? The derivative of sine is cosine. It's positive cosine. The antiderivative is negative. Moving back and forth takes practice. So the derivative of sine is cosine. And then I have dt on the end. And that's really good because that's what's right here, isn't it? It's exactly what the other portion of my expression represented. So I can replace the 1 plus sine t with u in the denominator. And I can replace the part that's circled cosine t dt with du. You can put it in the numerator or you can put it afterwards, either way. I tend to put mine afterwards, but either's fine. And then that should look like something you know. What is the antiderivative of 1 over u? ln of? Close. Absolute value of u. Nobody said it, but I know you know. Plus c, right? Yes, it is plus c. All right, let's take a look at this then. So I'm going to replace the u with the 1 plus sine t, and you guys know that. We've done this several times now. And I want to contend to you that it's perfectly fine if you leave it this way, but you could also see it written, and perhaps would more likely see it written in the back of your book or something else, like this. Why would you possibly be allowed to remove the absolute value signs and just simply use parentheses instead? Why could that happen? Yeah. We talked in class at one point about sine of t. I think it was our last class, actually, that sine of t has values, if you remember the curve from trig that goes up and down, right, that sinusoidal curve. It goes from -1 to +1, and it just keeps doing this oscillating pattern. So the very most negative that sine can be is -1. And what happens when you add -1 to the 1 plus at the beginning of this? You get 0, right? So I never get 1 plus sine t to be a negative number, which means the absolute values aren't necessary. They are not incorrect if you leave them there, but they aren't necessary to be there either. Does that make sense? Okay. All right, we have one more problem we're going to take a look at, and I want to in particular take a look at it because what's different about this problem? Yes, I have limits of integration. It's what we call a definite integral. And we haven't done one yet in this section, so I want to make sure that you remember that process. So the initial process doesn't change. The first thing we're going to do is figure out, do I use u substitution? Is there something else going on there? And so what do you think? What are we going to do? The whole top?
The middle part.
The part in parentheses?
1 plus ln of x.
That sounds good. So if I do that, whoops. What is du?
U for dx over x.
Okay. Or 1 over x dx, right? So if I deal with it this way, that's great. That's what I have, isn't it? I think I took care of every component except for the fact that this is squared. That's okay. So I can rewrite this as the antiderivative of, well, u squared du, right? Notice what I didn't do. I didn't put the 1 and the e back in that Emily noted from before, did I? Do you know why I didn't do it?
Because you have to change with the du.
Yeah. So that 1 and that e, that was specific values for the variable x. And I changed it into a different variable, didn't I? My u does not have the same values of 1 and e. There are two ways to handle that. One way, and this is the way I'm going to do it, let me tell you what I'm going to do, is that we're going to work the whole problem just like it is without the numbers 1 and e. We're going to turn everything back to x's in the end, and then we're going to plug the 1 and the e in. That's one way to do it. Okay? The other way to do it is, right now, what you could do is you could plug in the 1 and the e into this equation for u. U is equal to 1 plus ln of x. So I could take the number 1 and plug it in and say 1 plus ln of 1, and I would get a number, and that number I get would become the lower limit. And you may have seen a professor do that before as well. Either one's fine. To me, I just do all of my substituting and changing numbers at the end anyway, so I don't deal with it in midstream, basically. I do all the calculus first, and then I'll do all of the algebra at the end. So I'm going to handle it from that perspective. So what is the antiderivative of u squared? You guys know we already did this today. 1/3 u cubed. Good. And I actually don't need the plus c here. Why? It's a definite integral. I'm going to be plugging numbers in here in a minute anyway, right? And if I did have the plus c, I would end up with a plus c and a minus c, and they would cancel each other out anyway. So I don't need the c in. I do need to change it back into u, though. So I've got 1/3. I'm sorry, to change the u back into x. And then I have the natural log of x cubed. And I need that to be evaluated, like we said, at the e and at the 1.
What happened to the 1 plus?
Oh, I left them off. Thank you for asking. We're going to fix that. 1 plus ln x. Thanks, Emily. That's cubed. And there's my e. There's my 1. All right, good catch. Now we're going to plug the numbers in. So I'm going to move over here because I need some more space. So we've got 1/3. I have 1 plus the natural log of 1. All of that is cubed. So we'll do that in a minute. And then I subtract 1/3. I have 1 plus, I said it wrong. The first one's an e. Plug them in the right order. That would be good. Natural log of e. The other one is 1 plus the natural log of 1, and then cubed. Is that all good? Looks like it. What is the natural log of e? 1. That's a nice number, isn't it? All right, so over here, I actually have 1/3. I have 1 plus 1 cubed. And then what is the natural log of 1? It is 0. So this part is 1 plus 0 cubed. Is that all good? All right, because we're almost done. I'll just go ahead into a blank screen over here. So I had 1/3. We had the number 2, right? And what's 2 cubed? 8. So this is 8. Then I have minus 1/3 times, well, 1 actually. So this becomes 8/3 minus 1/3, which looks an awful lot like the number 7/3. Not a trick question at all. So this definite integral has the value 7/3. Any questions on that? Okay.